Y11 magnetic field. This is a three-dimensional plot showing the unit vectors of a Euclidean space, and I'm showing the relationship among velocity, charge, and magnetic field, and the magnetic force due to the motion of a charged particle inside a magnetic field. We have positive charge Q and negative charge Q. If I write Q, it does not state that it is positive. Even though I put plus Q, sometimes I help you to, it is a positive, but plus Q does not mean it is a positive definitive. You should be very careful. Q is a real number that can be either positive or negative. Okay, the SI unit for the magnetic field is Tesla. You have to memorize, and it can be converted in terms of simpler units. And there is a non-SI unit. This Tesla. This Tesla is not a company. It is a magnetic field unit. Tesla is a very strong. This is a very large number. So usually we use Gauss. Gauss is much weaker by 10,000 times. All right. The magnetic field charge Q under the magnetic field charge Q moving with the velocity experiences the magnetic force. On the electric field, charge Q experiences magnetic electrostatic force. And sum of these two forces is called Lorentz force. And you have to remember how to compute the cross product. And V and B are two vectors, and there is always a single plane on which both V and B are placed. And V cross B is perpendicular to both the vectors. And from V to B, there is an angle theta, and this magnitude is the area of this parallelogram. In mathematics, parallelogram can be drawn only in the dimensionless plane, but it is a physics. It is a velocity and magnetic field. They are absolutely different dimensions. So, however, there are two ways of defining the cross product. Our choice of the cross product is from V to B. You sweep your fingers except for the thumb, and it should be right hand instead of left hand. Then the direction of thumb determines the normal vector. There are two normal vectors, but we choose this normal vector. The kinetic energy of a charged particle moving in a magnetic field without the presence of an electric field, if there is no electric field and magnetic field is all present only, then the kinetic energy is conserved. Kinetic energy is conserved. Why? Work kinetic energy theorem. Magnetic force is Q V cross B. And the power is FV, and Q V cross B dot V. V cross B is perpendicular to B. Therefore, this scalar product is always 0. No, it is different. F dot V equals 0. dt equals F dot dx. What's that? That is the dw. Work is 0. And the work kinetic energy theorem says that this is the change in kinetic energy. Because it is 0, kinetic energy is invariant. Next, magnetic force applied to a charge Q moving with the velocity v is defined like that. What happens if I flip the sign of a charge? Then force is flipped. What happens if I change the sign of velocity? Again, the force is flipped. If I replace the charge and velocity, both of them simultaneously, then minus minus becomes a plus. Therefore, plus q moving with v and minus q moving with minus v, they experience the same magnetic force. Next, we consider crossed field. Crossed field is electric field and magnetic field are perpendicular to each other. We first look at this expression for the Lorentz force. First of all, Q times electric field is electrostatic force. Q times V times B is the magnetic force. Therefore, electric field and VB must be of the same dimensions. The reason why we use the different dimensions is that it is due to the history. Electric field that has been studied and the magnetic field that has been studied, they were studied independently. They didn't know why they are closely connected. Einstein told us that they are closely related. And actually, magnetic field and electric field, they communicate each other. However, historically, people didn't know about that. So our modern form of expressing the magnetic field is not B, but CB. If I multiply the speed of light to the magnetic field, then I have to divide the velocity with the speed of light. In this way, V over C is dimensionless, and electric field and the CB, speed of light multiplied by the magnetic field, they are of equal dimensions. Okay. Anyway, they are the same. Whether I multiply, it is just 1, is a C times 1 over C. So for the time being, forget about this and just concentrate on this term. We have across the field, E field and B field, E field and B field, either this or that, they are perpendicular to each other. In that case, we can think about the situation that electric force and magnetic force cancel exactly. Then this one indicates that E equals minus V cross B, or E equals B cross V. Haha, these two are perpendicular. So we can expect that we just like what we learned for the unit Cartesian basis vector, they construct the cyclic triad, the three basis vectors of the Euclidean space. They are perpendicular to each other, and their unit vectors satisfy this situation. And we can always construct a unit cube whose size are E1, E2, E3, something like that. In similar manner, we can think about the E field, B field, velocity. These three can construct a set of three basis vectors in the Euclidean space. Anyway, if they are all of them, these three are perpendicular to among one another, then the magnitude of the electric field, because the sine theta becomes 1, electric field is the same as velocity, magnitude of the velocity, multiplied by the magnitude of the magnetic field. Next, we consider Hall effect. And long time ago, in 1879, Irving Hall was a graduate student. He was writing doctoral thesis. He was just about to get his PhD degree at Johns Hopkins University. He discovered a very interesting thing. Until then, people just ignore the difference between ignore the situation whether it is a charged particle making current inside a wire is a positive or not. An actual experiment carried by this Hall, a graduate student Hall, carried out this experiment. He applied the same magnetic field. He didn't know whether the current is produced by a positively charged carriers or negatively charged carriers. He didn't know that. Anyway, there was an ampere meter who can measure the direction of the current at that time. So ampere meter states that current is flowing along a certain direction. Nobody knows what the charge carriers were made of. At least they were able to measure the ampere with ampere meter, measure the direction of the current and the magnitude of the current. And he applied the magnetic field, current, they were fixed. Under the magnetic field, charged particle, if it were positive and if it were negative, charged particle flows along the same direction, V, as the direction of the current. If it is a negatively charged carriers, in order to produce the current to the same direction, the velocity of the negatively charged particle must be minus V. All right, this is a plus Q positive with V, and this is a minus Q with minus V. We just learned that the magnetic force applied to plus Q moving with plus V, and magnetic force applied to minus Q with minus V, they were the same. By applying that idea, graduate student Hall expected that whether it is a positively charged particles or negatively charged particle, both of them accepts the magnetic force along the same direction. That's very important. positively charged particle will be accumulated on the upper side in the wire, and even in the case it is a negatively charged particle moving along the opposite direction, this charged particle also moves forward to the same direction. As a result, plus charges will be accumulated in this side. That means because the sum of the charges should be the same, so the bottom part will be charged with negatively charged particles. In this case, it is bottom part will be positively charged and upper part will be negatively charged particles. And he used a voltmeter to measure the potential difference between the top and bottom. And he indeed measured that this is true and this is wrong. Benjamin Franklin introduced the charge sign with positively charged particle is flowing, and he was wrong. And everybody was wrong. And Hall is the first person who found that the charge carriers are negatively charged. Oh, so everything must be flipped up opposite direction, but we have written a lot of materials, textbooks and applications, so there is no way to change it, flip the sign of the charge. So this is the history that unfortunately electron has been chosen as a negatively charged particle. If we knew that for the first time before this, well ahead of this, if we knew that the electron is negatively charged, then we could have a corrected theory that electron's charge is a positive. That is the most natural. But unfortunately, it was too late. So we keep using wrong sign of electric charge. Next, we consider the motion of a charged particle. Perhaps if you learn physics in high school, then you learn that inside a magnetic field, the charged particle makes a uniform circular motion because the kinetic energy is conserved. But in general, it can translate along a perpendicular direction too. In general, under the magnetic field only, it is making a helical motion. It is not DNA, it's a helical motion. But we can always make a Galilean transformation to catch it up. In that case, in the frame, there is a frame in which this charged particle makes a uniform circular motion. Okay, the shape of this path and shape of this path looks different, but they are correlated. In a certain inertial reference frame, it is a circle. However, there is another inertial reference frame in which the circle can be seen as a helix. Let me solve this problem completely. We have an experiment in which velocity of a particle is like that, and along the direction E3, it has a V parallel component that is uniform. We don't know what the electric field or magnetic field. We assume that both the electric field and magnetic field are constant. So there is a constant motion along the z-axis, but on the XY plane, we can see it is circulating. It is making a circular motion. If you put your eye on this side, then it is a circular motion. Okay. There are useful constraints. This phi, uniform circular motion on the XY plane. So phi should be a linear function of time. Because of that, phi dot time derivative should be minus the theta. Theta, it should be phi, right? It should be phi. It should be phi dot. And actually phi is omega t time derivative, that is omega. So omega is written here. And the direction is toward the center. And V perp, this is a V perp. V perp is tangential direction on the XY plane. So V perp is a radius r times frequency omega. What is the net force of the charged particle? Because we are not able to find what E and B, we are not able to apply this QE plus V cross B, the Lorentz force. Instead, because we know the velocity explicitly, we take the derivative of velocity to find acceleration and multiply the mass to find the net force. So velocity V, here this is constant, so V dot should be V perp, that is constant, E phi dot. So E phi dot is about this one. So I substitute minus omega E rho. Again, we use this relation to simplify this. So we have minus mv perp squared over r. So this force is toward the center of a circle on the XY plane. That's fine. It's a uniform circular. It is the same as that of the uniform circular motion. Now, let's see. If electric field exists, then this contribution must produce an acceleration. Is there any acceleration with the constant magnitude? Yes, this has a constant magnitude, but direction is keep changing. Direction changes, keep changing the direction. So it is impossible to have electric field. Okay, so forget about the electric field, and let's think about the magnetic field, how to create the magnetic field to reproduce this force. This V is decomposed into two pieces as was told previously, using this velocity. Cross magnetic field must be this one that has been obtained by computing F, that is m double dot x. Okay, we don't know what B is, so why don't we substitute arbitrary expression? For simplicity, we use Cartesian components. They are constant vectors. Therefore, B1, B2, B3, uniform field, so B1, B2, B3 must be constant. First of all, cross product with the parallel component along the z-axis will give this. By the way, this is perpendicular to B1E1, B2E2, perpendicular to this because this V cross B. However, still, this is a constant. This is constant. Acceleration that is not constant at all. So we get rid of this contribution too. Therefore, the only remaining piece is this contribution. So V per contribution to the magnetic field will give explicit expansion. Haha. I told you we have to get rid of this. That means B2 equals B1 equals all 0. B1 and B2 must not appear here. So B1 and B2 must be killed. And the only contribution, we are happy with this. By the way, if we write in this way, the result is positive sign QV per B3. However, in here we have negative sign on it. So it's better to choose the basis vector along the opposite direction of z-axis, the negative z-axis, to be the basis of this. All right, if I substitute this value to the magnetic field, then I have this relation. From this, we can determine the magnetic field that is along the minus E3 direction. The magnitude is determined like that. From this, I can also choose determine the frequency in such a manner. Next, it is a trivial problem. Electric field and QE and QV cross E, V cross B, the magnetic force, electric force, just train by yourself. Next problem, 6. Wait a second. Okay, let me finish this. Let me finish this problem 6. We have charged plates. We assume that it is an infinite plate, and somewhere there's connected like that. There's a horseshoe part of the horseshoe magnet. So we assume that this part is very large. There is a uniform magnetic field. Magnetic field comes out of the North Pole to the South Pole. So this is a kind of crossed field. We don't know what the electric field, but electric field is being emitted if sigma is a positive. If sigma is a negative, then electric field comes in. First of all, the magnetic field is certainly along this direction. Okay. Electric field, I don't know. Substituting the B field, and velocity is given in here, that is uniform, so we can determine the relation. That means the electric field is along E1. Okay. The electric field due to an infinite plate is like that. In here, we assume sigma is a positive, then it is toward parallel to E1 direction. But if it is negative, automatically it will choose the negative direction. So this is a complete solution. And electric field due to the upper one, if it is positive, its direction is negative. So it is natural to have this. And we apply superposition principle to sum them. The final result is like that. Okay, so we find the electric field. Previously, we found it must be expressed as the magnitude of B and magnitude of B and E1. They are the same. Okay, we have the relation. This one is the same as this. And actually, sigma 1, sigma 2 have a multiple solution. So the answer is this, and we can vary sigma 2 in many, many ways. And I think you can solve this problem 7 with an easy way. This is yesterday we considered electric dipole, and this is carbon copy. This is magnetic dipole. Magnetic dipole moment is area of a circuit. There is a current I is flowing in this direction. In that case, magnetic dipole moment is I times area. This is not imaginary number. This I is a current. Current times the cross-sectional area of the circuit. And the direction is chosen normal to the plane when we choose the direction of current counterclockwise. So using this relation, we can find the torque is mu cross B and the potential energy. The shape is identical to what we have found for the electric dipole moment under electric field. We used the P cross E and minus P dot E. Remember, we studied yesterday. Okay, so it is a carbon copy of the calculation.